Hello, good morning. I SEEMA GARG, Associate Professor in Chemistry, SPC Government College, Ajmer. Today, video 128. It is for BSc Part 1, Organic Chemistry, Paper 2, Alkenes, Unit 2. In last video 127, we had seen some methods of preparation of alkenes. In continuation of methods of formation, today we will see dehalogenation of vicinal dihalides, physical properties of alkenes, stability of alkenes. Alkenes we can prepare from dibromoethane. It is a dehalogenation in presence of zinc dust, alcohol. It will give us ethane plus zinc dibromide as a byproduct. Propylene dibromide also give us corresponding propene in presence of zinc dust and alcohol. This method is not a useful method for the preparation of alkenes since the dihalides needed for the purpose are themselves prepared from alkenes by the addition of halogens. However, it is useful for the purification and protection of double bond mechanism. E2 mechanism. Here, zinc is trying to abstract bromide and second bromide is trying to eliminate from the alkene. So we will get zinc dibromide and propene as a product. So it is a E2 mechanism because reagent and reactant both are taking part and transition state will form and then product will be obtained. Physical properties of alkenes. State, smell and color. C2 to C4 are alkenes are in gaseous, C5 to C17 are in liquid, C18 are solid, and all of these alkenes are colorless. Smell, only ethene gas having pleasant smell, while other alkenes are odorless. Solubility. Alkenes are also usually non-polar or weakly polar, insoluble in water and other polar solvents. While soluble in non-polar solvents such as benzene, carbon tetrachloride, petroleum ether, weakly polar solvent ether. Density. Density of alkenes are increasing with their molecular mass. Their boiling point increases with molecular mass. Branch chain alkenes have lower boiling point than straight chain alkenes. Melting point. Melting point of alkenes are higher than those of the corresponding alkanes. This is because of electrons of double bond are more polarizable than sigma electrons of single bonds. As a result, intermolecular forces of attraction are stronger in alkenes than in alkanes, and hence alkenes have higher melting point than corresponding alkanes. Moreover, cis-2-butene, it having lower melting point compared to trans-2-butene, it having higher melting point. because of close packing. So this is due to transalkene being symmetrical packed more closely in crystal lattice than the cisalkene molecules which are less symmetrical. Dipole moments. Dipole moment usually trans-to-butene having 0, trans-to-pentene having slightly higher, and cis-to-butene having more dipole moment. Relative stabilities of alkenes. The stabilities of alkenes have been related to their hits of hydrogenation. The hydrogenation of alkenes is an exothermic reaction. Heat of hydrogenation is the quantity of heat evolved during hydrogenation of 1 mole of alkene. See here, alkene. Here, pi bond is cleaved, and in hydrogen molecule, hydrogen bond, sigma bond is cleaved. For cleaving of this pi bond require only 60 kilocalorie per mole energy, whereas this hydrogen require 104 kilocalorie per mole. So overall is 164. Whereas when this alkene is formed, two new sigma bond is forming. So it will evolve 97 multiplied with 2, 194 kilocalorie per mole energy. So total energy obtained heat of hydrogenation is 194 kilocalorie per mole minus 164 kilocalorie per mole. It is about 30 kilocalorie per mole. The heat of hydrogenation can be measured and used for the relative stabilities of alkenes. Stability is directly proportional to 1 upon delta H or inversely proportional to delta H value. See here, ethene molecule, it will evolve 32.8 kilocalorie per mole, whereas propene will evolve 30.1 kilocalorie per mole. So here, propene having delta H value lower than ethene. So propene is more stable compared to ethene. Means we can say in other words, propene is 2.7 kilocalorie per mole more stable than ethene. It can also be explained on the basis of hyperconjugation. See here how this, due to this hyperconjugation, this molecule having resonating structure, so this propene is more stable. Thus, the substitution of hydrogen atom of ethylene by methyl group lowers heat of hydrogenation and increases its stability. See here, these are the ethene, propene, isobutane, then tetramethyl ethene. So this molecule having the heat of hydrogenation. So here the lowest is tetramethyl ethene. So tetramethyl ethene is more stable and ethene is less stable. Orientation of alkyl group. The trans isomer is more stable than the cis isomer as there will be less steric hindrance and van der Waals strain in trans isomer. See here, this having lower value of delta H, trans isomer, and cis isomer having higher value. Thank you very much for today's lecture.